So what is a logarithm? I'm going to answer that question, and I'm going to try to show you why logarithms are useful, and we're also going to look at the graphs of logarithms. Alright, so with exponential equations, we've had things like this. 2 to the x power equals 8. And that is actually a very easy question, because I know that 2 to the x is the same as 2 cubed, and since I've equated the bases, I can drop those bases and let x be 3. And we know that 2 cubed is 8, so that equation is pretty easy to solve. But now if I look at something like this, 2 to the x equals 9, I gotta think, okay, now 9 is what power of 2? Well, 2 cubed is 8. 2 to the 4th is 16. So that would mean x has to be somewhere between 3 and 4, but I don't know exactly how to do that. And that is why we care about logarithms. So we can define logarithms, and there are a lot of ways to define it, but we'll define it like we do in algebra as the inverse function of the exponential function. So we say the logarithm base a being the base, and we write it as this, f of x equals, that's log subscript a x. Okay, that's read as log base a of x, or sometimes we say it's just written as log base a of x, is the inverse function of the exponential function f of x equals a to the x power. So in other words, these things undo each other, and an easy way to remember that is that we say that a to the x power equals y if and only if log base a of y equals x. Okay, and that is the key relationship. This is what you need to memorize. A to the x equals y implies that log base a of y equals x, and vice versa. Here are a few key terms that you need to keep in mind as you're going through these, and I think it'll make these mysterious objects become clear. Alright, so here are what they are. First is you gotta think inverse functions. In other words, these undo each other. The logarithm is the inverse function of the exponential function. The exponential function is the inverse of the logarithmic function. They undo each other. Secondly, when you see log base a of y, you need to think what power of a is y. So for example, if I said log base 3 of 10, I need to think what power of 3 is 10. 10 is 3 to the what power, and that's what you have to always consider. Thirdly is you think about the whirlwind. And what I mean by that is converting log to exponential or exponential to log, as I say log base a of y equals x. And over here you can see that a to the x equals y means the same thing as log base a of y equals x. And on the other side, a to the x power equals y. Okay, so the whirlwind kind of helps you undo these things or convert a logarithmic to an exponential, exponential to logarithmic. And we're going to practice this now. Okay, so let's look at an example. Okay, so here for example 1, I want to write the following logarithmic statements as exponential statements. So in other words, we're undoing the logarithmic part. Alright, and so here at part A, I have log base 4 of 64 equals 3. And I'm wondering, is this a true statement? This log thing is confusing here. Remember, these are inverse functions, right? We also said that we have to consider what power of 4 is 64. And we lastly said, let's think about the whirlwind. And the whirlwind said that this would be 4 to the third power equals 64. 4 to the third power equals 64. And remember, what power of 4 is 64? It's the third power. So this is a true statement. Log base 4 of 64, the answer to that is simply 3. It reduces down to 3. Because again, 64 is the third power of 4. Alright, let's try part B. We have log base 10 of, what number is that? 10,000 equals 4. Okay, is this a true statement? So what I'm trying to think is what power of 10 is 10,000? Well, let's do the whirlwind. 10 to the fourth power is 10,000. 10 to the fourth power equals 10,000. And that's a true statement. And again, remember, the logarithm reduces to what power of 10 am I talking about? I'm talking about the fourth power. Okay, lastly, 5 to the fourth power equals 625. 5 to the fourth power is 625. And this is a true statement because 625 can be written as 5 to the fourth power. So if you see something like this, as an example, what is log base 11 of 121? Well, I'm thinking in my mind, what power of 121 is 11? Well, it's the second power, right? This is equal to 2. 11 squared is 121. Let me give you a tricky one. Log base 36 of 6. Again, I'm thinking 36 to the what power gives me 6, right? If I did a whirlwind, so let's just put a y here, for example. And if I do my whirlwind, 36 to the y power equals 6. Oh, this is something we did when we were solving elementary exponential functions. That's 6 squared to the y power equals 6 to the first. So that means that 2y equals 1, or y equals 1/2, which totally makes sense because remember, a 1/2 power means a square root. 6 is 36 to the 1/2 power. I could have written that out as 36 to the 1/2 power equals 6. And that's exactly what the logarithm is saying, right? So this thing reduces down to just 1/2. I hope that makes sense. Now let's see if we can go the other way. Alright, so now for part 2, example 2, we want to write the following exponential statements as logarithms. So for part A, we have 8 equals 2 cubed. And I want to write this as a logarithm. Remember, I can still do the whirlwind. I can say log base 2 of 8 equals 3. That says log base 2 of 8 equals 3. Is that consistent with what we were thinking about earlier? Yes, because remember, we were saying if you take this middle term, the 8, I have to think 8 is what power of 2? Well, it's the third power of 2, so that makes sense. Alright, so moving on to part B, we have 3 to the 4th power equals 81. Again, I'm going to do my whirlwind. That is log base 3 of 81. My thought is 81 is 3 to what power? It's the 4th power. Alright, so lastly we have 16 equals 2 to the 4th. So use my whirlwind again. I have log base 2 of 16 equals 4. And that's exactly right, because what power of 2 is 16? 16 is 2 to the 4th power. So the power of logarithms, the reason they're useful is because a logarithm shoots out the exponent, right? So we started out looking at an equation like this, 2 to the x power equals 9, and I said, wait a minute, I don't know how that works because I just know x is somewhere between 3 and 4. Well, now I can rewrite this. I have log base 2 of 9 equals x. And so there's my answer. If I can figure out how to calculate log base 2 of 9, I have found the power of x such that 2 to that power gives me exactly 9. And that's the power of logarithms. They help fill in the gaps in my exponents. They also help take exponential equations and turn them into linear, right? So if I add a variable exponent, now I don't. X is not an exponent anymore. Let's look at the graph real quick. Alright, so if you remember with exponential graphs, we had two cases. We had one where our base was between 0 and 1, and we had another case where a was greater than 1. If a was between 0 and 1, then my graph looks something like this. I had a horizontal asymptote, pass through at 1 at the y-intercept, and then kind of go up like that. For a greater than 1, it was the opposite. I had a horizontal asymptote going out to negative infinity to approach 0, cross at 1, and then it would shoot up like that. Now remember, we said that the logarithms are inverse functions. The graphs of inverse functions are reflections about the line y equals x. And I think that makes sense because in the inverse functions, the y's and the x's trade places. So for a between 0 and 1, we can see that for my exponential graph, as x approaches infinity, y approaches 0. So in my logarithmic graph, it's the opposite. As x approaches 0, y approaches infinity. So I have an asymptote going like this. I'm going to cross right here, hit 0 at 1, and then kind of plateau out like that. It's not exactly plateauing. It's going out to negative infinity just very slowly. We cross the point 1, 0. There's a graph of f of x equals log base a. Now a similar thing happens for a greater than 1. It's just a little easier to visualize the reflection. It just goes like this. And so again, we cross at 1, 0, and there's the graph for f of x equals log base a of x. Okay, so this is a good introduction to logarithms. We have other things to consider. There's a lot of interesting properties, and we're going to use logarithms to solve some pretty complicated equations. If you have questions on this, on the basics, please let me know. I'd be glad to help you. And thank you for watching.